A property of plane convex sets. I am Eduardo Rivera Campo, and this is joint work with Jorge Urrutia Galicia. Given a collection of plane compact convex sets with pairwise disjoint interiors, we say that a line L separates a set A in F from a subcollection H of F if A lies in one of the closed half planes defined by L, while every set in H lies in the complementary half plane. And this small illustration, the red set A is separated by the line, the blue line L, from the subcollection of green subsets. Twerberg proved that for each positive integer k, there is a minimum integer f of k such that for every collection f of k or more plane compact convex sets with pairwise disjoint interiors, there is a line that separates one set in F from a subcollection H of F with at least k sets. Hope and Kachalski gave bounds for the value of f of k and proved that 3k plus 1 is less than or equal to f of k, and f of k is less than or equal to 12k minus 1. The upper bound translates into, for every collection f of n compact convex sets with pairwise disjoint interiors, there is a line that separates one set in F from a subcollection of F with at least n plus 1 over 12 sets. In 1993, together with Jeno Torokchik, we proved that in any collection F of pairwise disjoint compact convex sets in the plane, there is a pair of sets A and B such that any line that separates A from B separates either A or B from a subcollection H of F with at least n plus 28 over 30 sets. N plus 28 over 30 is certainly less than n plus 1 over 12, but in our result, it's any line that separates A from B, separates also either A or B from at least n plus 28 over 30 sets. So here we have a small family of convex sets, two sets A and B, one line that separates A from 8 purple sets. Here is another line that separates A from only 4 sets, but separates B from 8 purple sets. Here we give a higher lower bound of n over 18 sets for the size of H for any collection F of n greater than or equal to 2 sets. Our proof is based in the following property of convex polygons. Let P equals to P1, P2 up to Pn be a collection of pairwise disjoint convex polygons in the plane. There is a collection R equals to R1, R2 up to Rn of pairwise non-overlapping convex polygons such that for I equals 1 to n, Pi is contained in Ri. For I equals 1 to n, each side of Ri supports a side of Pi. And the total number of sides among polygons R1, R2 up to Rn is at most 9n minus 9. Here's a little example, a collection of 7 blue convex polygons with a total of 80 sides, and a collection of 7 red polygons, each containing a blue polygon. Each side of a red polygon supports a side of a blue polygon. And the total number of sides in the red polygons is 24, which is less than 9n minus 9. If we drop condition 2, that each side of Ri supports a side of Pi, then the number of total sides can be reduced to 6n minus 9, as asserted by this theorem by Edelsbrunner, Robinson, and Shen. So in this example, now we have 7 red polygons, each containing a blue polygon. Some sides of a red polygon supports the side of the blue polygon or the corresponding blue polygon, but some sides of a red polygon support no side of the corresponding blue polygon. And indeed, the number of the sides, total number of sides reduces to be less than 6, 9 minus 9. And the total number of slopes is 16, which is less than 3n minus 6. The sketch of proof of our result, our property, we say that a side S of a polygon P in the collection P is reducible with respect to P if it vanishes before reaching the interior of a polygon Q in P when it is translated in the direction orthogonal to S and away from P. Here's an illustration, a polygon P and a side S of P. And when it is translated away from P in the direction orthogonal to S, it never reaches the interior of any other polygon in the collection. So with this concept in mind, a collection R equals to R1, R2, up to Rn, satisfying conditions 1, 2, and 3, can be obtained from P equals to P1, P2, up to Pn as follows. One at a time, banish a reducible side S of a polygon Pi in P. So here's the first step of the polygon we use on the previous illustration, the side we use on the previous illustration. And when this is banished, we can choose another side, in this case, this side, and also banish it. And so we continue, repeat until no polygon in P has a reducible side. And then we get the collection R equals R1, R2, up to Rn. It is clear that each polygon P is contained in the corresponding polygon Ri, and that each side of a polygon Ri is supported by a side of Pi. When we banish a side, we never create new sides. So we banish a side that is also in Pi, and Spanish, but we never create new sites. And we claim, without a proof here, that the total number of sites among the polygons R1 up to Rn is at most 9n minus 9. Here's a lemma which we'll use in the main proof. Let P equals to P1, P2 up to Pn be a collection of pairwise disjoint convex polygons in the plane. Then there is a side S of a polygon Pi such that the line supporting S separates Pi from a subcollection F of P with at least n over 18 polygons. So here we have a family of convex polygons, and we have shown one red polygon and a side of it, S, such that the line that separates S, the line that supports S separates the polygon, the red polygon, from these green polygons. Here's how the proof goes. Let P equals P1 up to Pn be a collection of pairwise disjoint convex polygons in the plane, and let R equals R1, R2 up to Rn be the polygons satisfying conditions 1, 2, and 3 found as in the previous result. So here we have a collection of blue polygons with a certain number of sides, and the corresponding collection of red polygons, each containing a blue polygon. Each side of a red polygon supports a side of a blue polygon, and the total number of sides among the red polygons is at most 9n minus 9. Let L equals L1, L2 up to Lm be the multi-set of lines supporting the sides of each polygon in R. we say that it might be a multiset because we include C copies of a line L if L supports C sides of C polygons in R. So here in this figure, I put only the 4 lines supporting the 4 sides of the middle polygon, the red polygon in the middle. And on this slide, I have put all the lines supporting all sides of the red polygons. So we can associate a unique polygon Ri of k to each line Lk in L in such a way that the side of Rik is supported by the line Lk. For k equals 1 up to m, let h minus k, h sub k minus be the closed half plane determined by the line Lk that does not contain the set Rik. So here it is, I have this polygon Rk and a line supporting one of its sides. And well, the closed half plane defined by this line that does not contain the polygon Rk is h minus sub k. Now we define a bipartite graph F with one vertex for each polygon R, one vertex Bj for each polygon Rj, and one vertex Wk for each line Lk. The graph has an edge between a vertex Bj and a vertex Wk if the polygon Rj is contained in the closed half plane h minus k defined by the line Lk. That is the closed half plane that does not contain the polygon R associated with this line. Remark, for each pair of polygons in the plane, there is disjoint polygons in the plane, there is at least one side S of one of them, such that the line supporting S separates Ri from Rj. So in here we have 2 polygons, and indeed it's there is one line that supports a side of Rj that separates Ri from Rj, and it's really the only line supporting a side of one of these polygons that separates the 2 polygons. Then the graph F has at least one edge for each pair of distinct polygons. This implies that the average number or the average degree of the vertices W is at least n choose 2 over m, which is at least n choose 2 over 9n minus 9, which is exactly n over 18. So there is a vertex, there has to be a vertex with at least this degree. This means that the line Lk separates polygons polygon Rik, and therefore the polygon Prk, which is contained inside, from at least n over 18 polygons in R. By condition 2, line Lk supports the side of the polygon P sub Ik. This is our main theorem. In any collection C of pairwise disjoint convex sets in the plane, there is a pair of sets A and B such that any line that separates A from B separates either A or B from a subcollection F of C with at least n over 18 sets. So let's see be such a collection of pairwise disjoint convex sets in the plane, and for any line in the plane, let any line L in the plane, let T minus sub L and T plus sub L be the number of sides in C lying to the left of the line L and to the right of the line L, respectively. For I this different from J, let Li sub J, let Li sub Ij be a line separating Ci from Cj, for which the maximum of these two numbers is as small as possible. So the line separates two sets, Ci and Cj, and is the line that separates one of them from the least number of from the smallest number of polygons. Now we take a triangle T containing all sets in C and define for each I equals 1 to n, we define a polygon PI, which is the intersection of the triangle T with the intersection of all closed half planes defined by the lines Lij that contain the convex set Ci. Then, for I equals 1 to n, Pi is a convex polygon that contains the set Ci, such that each side is supported by a line Lij, or by a side of T. So for this polygon, this side is supported by a side of T, and the rest of the sides are supported by lines separating polygons in C. By our lemma, there is a side S of a polygon Pj such that the line Ls supporting S separates Pj from a subcollection of P1, P2 up to Pn with at least n over 18 polygons. Since no side of T separates two polygons in C, then this line has to be one of the lines of the form L of the form Lij. Now, by the choice of the line Lij, each line that separates set Ci from Cj separates either Ci or Cj from at least n over 18 sets in C. This is the reference of our paper, and I thank you very much for your attention.